Actually, I'm picking up topics that we heard yesterday on cold ion molecule chemistry, and also you already heard about the idea of doing this in the orbit of a Rydberg atom in the hot topic talk from Valentina. Many things might sound familiar. I will repeat them anyway because we have a lot of input here, so I think it doesn't matter. So while I'm waiting for the slides to come up, I can just do my introduction speech. I thank the organizers for inviting me, bringing me here. Really enjoying this meeting very much. I have a group in Leipzig where we actually focus on the properties of ultra-cold Rydberg atoms, studying exotic bound states, long-range Rydberg molecules, doing spectroscopy on them. But today I decided to talk about an ongoing cooperation with the group of Rydberg at ETH Zürich, where I have the historic connection. I was postdoc there for quite some time, and so we are continuing the experiments. So the experiments that I'm talking about today, they have been performed in Zurich. Mostly it's the PhD work of Katharina Höveler. This is what we heard yesterday from Heather, like the chemist's view of cold chemistry. It's just it doesn't exist because chemical reactions mostly are described by the Arrhenius law. So you're suppressed by an activation energy, and only when your temperature is high enough to overcome this, actually something's going on. So if you look at the reaction rate as your temperature approaches zero, it just goes to zero. And you are already aware from yesterday that there is the exception of barrierless reactions that, don't have a barrier. And these often or mostly involve radicals or ions. And that's why it's also obvious that these are of astrophysical relevance, because in interstellar space, typical temperatures in these interstellar molecular clouds are on the order of 10 to 50 Kelvin. So reactions with a substantial barrier just don't take place. So the reaction that we are studying and that I will mostly focus on is this reaction prototype that's been studied for a long time, H2 plus H2 forming H3 plus. And you can argue that this is the most fundamental reaction in interstellar space because you just need a hydrogen molecule that is ionized by a cosmic ray. And then this H2 plus within a few thousand or million years will find another H2 and form H3 plus. And this H3 plus is the universal proton donor. So it can react with another oxygen atom to form OH plus, and then with another hydrogen to form water, H2O plus. But also with carbon, it leads to the formation or initiates the formation of all these complex carbon-hydrogen chains that we also heard yesterday about. So let me give you a short description of how you can look at these barrierless ion-neutral reactions. All the numbers are for this example. So if we are at temperatures above 1 Kelvin, we can describe them classically. So you have a certain impact parameter, and once the reactants come closer than that impact parameter Bmax, it will be captured. That's why these are also called capture theories, and you will have a reaction. And if you do the math of this purely classically, you come up with the Lejeune rate coefficient, which, as you see, is actually independent of collision energy. So it's constant, and that's why even at zero temperature, the collision proceeds, or the reaction proceeds. Now, if we go to the quantum regime, and we heard a lot about S-wave scattering, so this is the theme here, when you have to consider that the angular momentum of the relative motion is quantized, then we have here the centrifugal barrier, which is now discrete and depends on your angular momentum. What one finds if one does the math here, and that was already done like 70 years ago, but I'm just taking the figure here from a paper from Gao in 2011, then you see that for a large range of collision energies, you exactly find the classical Lejeune rate constant. You just have these small oscillations around the mean value that come from the opening of channels when another partial waves become classically allowed. And at very low collision energies, there is, and this is in the S-wave regime, there's actually a sudden jump up by a factor of 2 from the classical value. And that factor of 2 was already predicted like almost 70 years ago in that publication by Vogt and Vanier, where they also already predicted those oscillations. And you would think that a prediction that was made 70 years ago surely has been tested by now and was seen, and actually that's not the case. Why is that the case? I guess here I don't have to explain you this, that for an ion neutral reaction, because we have a long range 1 over r to the 4 potential, it's much harder to reach S-wave scattering. In this very light system with a very low polarizability, the S-wave collision temperature corresponds to 9 millikelvin. If you compare this to the 10 microkelvin that we heard in Venice, it certainly looks warm or hot. But these are molecular ions, so it's much harder to reach these low collision energies. So, as I said, this reaction has been studied in great detail. So the first experimental data is here from the 60s, and then there are different theory and experimental collisions. And this is a review in this very important paper by Stefan Schlemmer and the late Dieter Gerlich, where they summarized all this and really showed or concluded that it follows the classical Langevin description from collision energies of an electron volt down to very low collision energies. So it's the prototypical perfect capture reaction with no reflection at all. Everything that goes in reacts, and that's important. It also happens on a single adiabatic potential energy curve, so there are no other states involved here. So here I have this that figure that is from 2016, so it's a bit old. But here we showed that in that interesting range of interstellar chemistry and in the quantum regime, there is no experimental data. And I'm just picking up here this what Valentina said yesterday. The problem is for example, merged beam experiments, that already a potential energy difference of a milli-electron volt corresponds to a difference in collision energy of 12 Kelvin. So it's just very hard to reach these experiments. So this brings me to the outlook of my talk. I first of all shortly summarize the idea of studying ion neutral reactions within a Rydberg orbit. Then I describe in a bit more detail our experimental setup, and then present you two scientific physical results that we have taken, namely study of the isotope effects in that reaction, and in the end, our go at confirming the Vogt and Wanier's prediction in that system. So I explained to you why it's very hard to study this with a real ion with H2 plus H2. So we study the reaction of H2 star, which star means that H2 is a Rydberg state reacting with H2, and you form H3 plus, and you get that additional electron that we ignore. And the idea behind this is really the Fermi model of independent colliders, so that in a reaction we can really treat the interaction of the electron with the reactant and of the ion core with the reactant as separate events. And this assumption is really, tested to an excellent level for reactions involving the electron. For example, in electron attachment experiments done by Dunning and Hottop and so on. And also in my core business, long-range Rydberg molecules, we use this assumption to describe the binding in these excited molecules really very high accuracy. So here we just take this other part of the independent collider assumption and say that if, so this here is the reactant, if the reactant reacts or does something with the ion core, then the influence of the electron is completely negligible. And it's easy to rationalize this if you look here, cartoonish at the orbital of an n equals 30 Rydberg state. Doesn't depend in which system, because it's quite universal properties. And here we have the capture cross section at 10 Kelvin. So you see that if this reaction happens, so this is when you are classically within the capture radius, then the electron is far away, and the probability of finding it there is small, and so the effect is negligible. So here's some numbers for actually 1 Kelvin. The capture radius for this reaction is 1.6 nanometers. So you see that's a factor of 30 or so smaller. And so also for this part of the independent collider model, this has been tested in that pioneering work by Deiglmayr and Chupka, where they showed that the rate constant for this reaction just become constant as you choose a sufficiently high value of the principal quantum number, so as you make that orbit large enough. And also Fernanda and Valentina, who are also in the audience, showed in a reaction of helium with CO, that this is a very well justified assumption. So this is one part. So we study that in a Rydberg orbit, which provides like a Faraday cage for the reaction. So there, the influence of external stray fields can be completely neglected because they are shielded by the electron. And then for actually now studying a reaction, we use the concept of a merged beam reaction setup. So we have two beams that propagate in parallel. And when you have two directions propagating in parallel, the collision energy is only determined by the relative velocity. And so we really can tune this through zero. And this is not so recent anymore. Experiments using this for neutral species in the group of Edna Vitius and Andreas Osterwalder. And so we took this and implemented this for Rydberg molecules and atoms instead of now neutral species, I mean ground state nuclear atoms. So here's the idea. We have a planar electrode structure. So this here is millimeter spacing, so really macroscopic because everything is just much larger if you work with Rydberg atoms. And if you are an ion trapper, then that might remind you just of a chip-based trap. Instead that here we apply static electric potentials, and if we specifically apply these static potentials on the order of 100 volt or so, then the electric field magnitude has a minimum here. It's actually a quadrupolar minimum, and we exploit here the strong linear Stark effect in the degenerate manifolds of Rydberg atoms. So this is static fields, and if we now modulate this field, we can just move around the minima here over the chip. And here is a small animation where you have your Rydberg atoms or molecules propagating, then you switch on the fields, and here we bring them to standstill within a few millimeters or so. So in these experiments, we don't want to bring them to a standstill, so instead we guide them and we bend our chip so that they make a 10-degree bend from the initial propagation direction so that we can merge it with the neutral beam. And we can also change the velocity of the Rydberg molecules via this method in a very controlled way, just by changing the frequency of the waveforms that we apply to this. And this, I mean, that's in the megahertz range, so that's not really challenging. So here a few experimental details. So we have our beam of ground state H2 molecules, and here we have another beam of H2 molecules. We excite H2 in a Rydberg state, and that's now a bit the annoying part if you work with hydrogen, that your first photon here is in the vacuum ultraviolet at 106 nanometers. So we generate this by 4-wave mixing of two visible photons, or a UV photon and a visible photon in a xenon jet. And then the next two transitions are more convenient, two visible photons from two other dye lasers. So in total, these are then 4 dye lasers that you need for that. And we take care by choosing the transition in the molecule in such a way that in every step we transfer one moment of h bar. So then when we end up in the Rydberg state where the ion core is really in the vibrational and rotational ground state, so it's an H2 plus molecule in V equals 0, N equals 0, then we end up in a Rydberg series that has F character, so high angular momentum, so it's long-lived and also has even a lower probability to be at the core and interact with the reaction. Then we have this traveling wave Stark decelerator, which is bent, and then here actually the reaction happens within a time of flight spectrometer, and this is another crucial part of our experiment, that we can control the reaction volume and the reaction time very precisely. So we apply a cleaning pulse that removes all ions which are there and that have already produced here in that part where the beams already merged. Then we switch the fields off for a variable time, typically like 5 microseconds, and then we extract all the products out of this volume onto our microchannel plate in a kind of Wiley-McLaren configuration. And just for the dimensions, it's a bit hard to see now with the color code, but our ground state pulse is much larger than the size here of the spectrometer, and the Rydberg molecules are really strongly localized in the center, so the reaction volume is very well defined here. And then we mass selectively detect the product ions, and if we look here at this reaction, H2 plus with H2, then the only charged product that we detect is H3 plus. You see that there's a bit of a background when we time shift the two valves relative to each other, so we just subtract this, and then we can really very precisely, accurately determine the number of product ions in that reaction. So that was more or less our status, or like 5 to 6 years ago. And then the first step of Katharina and her PhD thesis was to look at these reactions with deuterated species. So here, if we now react H2 plus with D2, then we get two products, H2D plus and D2H plus. And so in this case, there is really no discussion about the branching ratio. So that was something that we had a discussion yesterday in talk of Eric Hudson. So here, the reaction products are formed, and these are stable molecules. So we detect them, and we just compare these signals. And on this slide, experimental work of months is summarized. Because Katharina really looked at all these reactions, H2 plus plus HD, HD dot plus D2, HD plus plus HD, HD plus plus D2, D2 plus plus HD. And most of this require like changing lasers and doing characterizations and so on. And then also with careful numerical simulations and so on, we extracted these branching ratios for all these reactions. And the first thing that you can do to explain these branching ratios is just do a combinatorial model. So you just count how many ways are there actually to make up these products from the atoms that you had initially. And that gives you these ratios that are given here by these green bars and also in that list. And for this first one, which also the first one that we studied, it worked quite well. And then for all the others, it fails. And it's a bit surprising because these are actually the models that are used to model dynamics in interstellar space and also in cold plasmas. They really seem to use these kind of combinatorial models. Why was there no data on this before? Because only at our low collision energies, these two product channels dominate, and we can detect all products. And processes like charge exchange play no role because it proceeds on a single adiabatic surface. But it's the temperature range which is relevant for interstellar chemistry. So here kudos to Frederick Merkt, who came up with this model to describe what we observe. And basically, what we learn from this is that here you have very similar branching ratios for these type of reactions that look different. So in both cases, we produce HD2 plus and H2D plus, and we have similar branching ratios. So that was a strong hint that actually it only depends on the products and not on the reactants, what you get out. And so the thing that distinguishes the products is here, because all happens on the same von Oppenheimer surface, is just the density of states of your products. And so this expression, I mean, if you ever did transition state theory or so, then it might look familiar. So we have the density of states from the translation, from the symmetry number, so the number of indistinguishable nuclei in the molecule, from the rotation and the vibration. And this is all approximately in the high temperature approximation and so on. And so these vibrational constants, they scale with the square root of the reduced mass. The rotational constants, they scale with the reduced mass. So for the lighter molecule here, H2D plus, you see that this is more widely spaced than for HD2 plus. So that's just very pictorial here. And if we calculate the rates with this model, or the branching ratios have to be more precise, then we find these numbers, which were in almost all cases in very good agreement with what we observe experimentally. So there is a strong correlation between the observed branching ratios and the approximated density of states in the product channels. Now there are two ways that you can think of how to explain that statistical result. The one is that you have equilibrium, and this we can include here because neither in the entrance channel nor in the transition state there is like a local minimum, a longer-lived metastable complex or so that could equilibrate all these degrees of freedom. So we think that it's rather analogous to a sudden approximation, that you just project your initial phase space on your outgoing phase space, and then this is determined mostly by the density of states. But this, I think, remains maybe something for theory to really figure out why there is this strong correlation here between the statistical argument and what we see in the experiment. One thing that I didn't talk about is the collision energy, and we can control the collision energy in two ways. We can either change the temperature of the valve that produces the ground state molecules. So by changing this here by 100 degrees or so, we can change that velocity by 1,000 meters per second. And I already said that we can change the the velocity of the Rydberg molecules by changing the way we run the deflector and decelerator. It's very important to characterize exactly the velocities we have, and this we do here by two fast ion gauges just after each other. So the ground state packet propagates through these fast ion gauges and gives us these two signals. And by very simple modeling, we can extract from these two measurements the velocity distribution of our neutral ground state beam. And so we know exactly at which time, which velocity class is interacting with our Rydberg sample, which is very localized in the center here of the time of flight stack, as I said in the beginning. So this is a measurement. Now it's very small to read, so I'll read the axis to you. So this is Rydberg velocity, so the velocity that we program for the Rydberg molecules. And this is the mean velocity of our neutral beam. And you see that there's always an enhancement when the two coincide. So whenever when we cross relative velocity of 0, there's actually an enhancement of the reaction rate. That's something that we observed and published in 2016. So you see that it's constant for higher collision energy. If we now put that relative velocity into an energy, into a relative energy scale that we always express in Kelvin, but it's not a real temperature, then we see that it's flat as predicted by the Deiglmayr theory, and then it rises for low collision energies. And here we see an increase of maybe like 10%. And then Katharina was working hard, improving the statistics and the energy resolution, and this is basically how it looks like 5 years later. So now we have an increase to 30% and a much better statistic, so given by these error bars. So what's going on? Why is this so different? And is this really that factor of 2 enhancement that I talked about in the beginning for pure quantum scattering? Well, it's not. That's something that we already understood in 2016. So H2 in a rotationally excited state, so in J equals 1, which is ortho H2, has a quadrupole moment associated with the rotation. And so this quadrupole moment can align or anti-align with the reaction axis. And if that reaction is proceeding slow enough at low collision energies, it can lock onto the collision axis. And you just follow the more favorable reaction rate, so the reaction is faster. And that predicts an increase of the reaction rate over the Deiglmayr limit by a factor of 4. So quite far away from the 30% that we observe. And this is because we average over many collision energies. So what do we have to do to actually see that enhancement, this pure quantum mechanical effect? So in this measurements, we can just simulate, or it's a lot of cross-checks involved to simulate this, but we did this very carefully to simulate the contribution from the molecules in J equals 0 and the molecules in J equals 1, right? Because of the nuclear spin symmetry and because the two hydrogen atoms are indistinguishable, you have these two species of ortho and para H2 that do not interconvert. And so we, even in our ultra-cold beam, we always have both of them. And ortho H2, which is rotationally excited, has a molar fraction of 75%. So if we do the averaging over our distribution that we measure very accurately, we get these curves here. And you see that really the majority of the signal that we see, the enhancement, is due to ortho H2. And only that tiny bit here is that factor of 2 enhancement that you see for pure S-wave scattering. So what do we have to do to enhance this effect? We need a higher molar fraction of para H2. So we told this to our engineer, to Seppi Agner, who said, build us something that produces para H2. And he built something. And we said, so how do we know now that actually it is producing only para H2? So directly in situ in our experiment, we do laser-induced fluorescence spectroscopy. We excite the molecules either from J equals 0 or J equals 1 into an excited state. And by collecting the fluorescence, we can determine the ratio of the population in these two states. And because this is in situ, this is exactly what's reacting, what's taking part in the reaction. And well, there are Frank-Compton factors and so on involved. So we use that natural ratio of 75% as given and as benchmark. And then from this, we can extract that for one sample that he gave us, we have a molar fraction of 40% in there. And for another sample, the molar fraction of ortho is 20%. And so with these 3 samples, we did the measurements, or Katharina did the measurements. So you have already seen this. And then now in this measurement and the simulation, you see that now the contribution from the ortho, from the para H2, so this blue part here, becomes comparable to the error bars, which are statistical and systematic error bars. And then for this sample B, really we are now 3 sigma always statistically significant, that we need that contribution from para H2 to explain the observed enhancement of the reaction rates. And so the contribution here from auto is so much larger because that's more or less like a classical process, and it modifies the long-range interaction potential, and it just goes to much larger collision energy. So that's why the contribution is so much larger. You can also directly look at this by plotting the molar fraction of auto H2 against the observed enhancement rate, and just by a linear regression extrapolation to 0, we obtain here enhancement of 3%. Again, 3 sigma different from 0. So this is as good as we can do here, and now they're working with other experiments to elucidate this with a higher signal. But it's important to note that this is really a factor of 2 enhancement, and only in our experiments it diluted down to 3%, but over a much larger range of collision energies, because our energy resolution is broad. Just like in spectroscopy, if you have a broad laser, your maximum goes down, but the integrated line intensity stays constant. And so with this, I'll not read out the summary, but I would like to thank the people. So this is Katharina, who is now graduated, and that's really her PhD work, and the 2 engineers, Hans-Jörg Schmutz and Josef Agner, who are really essential to do all these experiments, and Frederik Merkt, in whose group this was done. And other people in the group, like Raphael Hahn, who's now taking over that experiment, Urs Hollenstein, Valentina, for discussions and contributions. So thanks for your attention.
Thank you, Johannes, for the nice talk. Let me ask first, when you said the statistical model is similar to the one that John Bohm proposed, with you mix all the states for the, you know, when they approach and they have all this spaghetti of states mixed in there?
Yeah, I'm not too familiar with that model, but certainly it's related to these universal models of Paul Julien to have a universal reaction that occurs with 100% efficiency. So we really just look at the density of product states. And I think that in the John Bohm model, there is the transition state that, or the intermediate complex which is formed, yeah, versus the sticky picture.
Very nice talk, Johannes. Yeah. So since the energy resolution seems to be a big part of the challenge here, so what are the prospects for further improving that?
Yeah. So if you remember that animation that I showed in the beginning, we start with a very cold, very localized beam here, and then when we switch on our potentials, so here, so this is cold. That's, I don't know, 10 millikelvin or something, and then you switch on this, and then you heat it up. And so we tried for a long time to just reducing these potentials, and it increases the energy resolution down to maybe 100 millikelvin, but that's basically where we are stuck. So we need to find a way to study this without a deflector and without that dosation, and there are ideas how to do that.
Roland, please.
Yeah, thanks so much, Johannes. A comment and a question. So I think what you showed, and the fact that this is statistical in the reaction, points rather to a sort of enough time in the reaction complex to really explore the entire phase space. I would guess so, at least. My question is, did you think about also anharmonic contributions? Because your statistical model here is really just a harmonic oscillator approximation and rigid rotor approximation. H3 plus is a very anharmonic system. So I'm wondering if that plays a role on this level of accuracy here.
Yeah, I mean, this is, you already answered the question. It does not, we think the goal is not to make a very accurate prediction, and we don't think that it would be more accurate if we now include anharmonicity, but just to basically roughly estimate the density of states. Actually, anharmonicity is not so bad because the total exothermicity here is 1.7 electron volts. 1/3 of this goes into the internal excitation. Or is it in translation? 1/3 goes into translation, 2/3 go into internal excitation. So here we end up with an energy of 700 milli-electron volts or so for the internal states. And so only the lower vibrational states are actually populated. So the anharmonicity there is not so strong. Rotation is a different thing, but yeah. So there is a very weak minimum here for H4+. here, which is not depicted on that cartoon or so, but really that is so submerged when you come in with that high exotomicity that there is, I mean, maybe, but we have no reason to believe that actually there is something formed intermediate complex. But it is a discussion that's going on in the literature for 30 years or so, and often also these isotope ratios are taken as an argument. Maybe there is charge exchange at large distances that scramble things already, and that's something that we know now is not the case. And so, yeah, but I think it's still something interesting to model for theory if theory is interested.
Yeah, I wanted to ask, HD has a dipole moment.
Yep.
Did you see any effects of that dipole moment?
Yeah, so Valentina, who's just sitting right behind you, did the calculation. So the dipole moment is 10 to the minus 4 in atomic units, and the effect is negligible. So she implemented the adiabatic channel model for the erection of an ion with a charge, ion with a dipole moment, and there's basically no significant effect.
I don't see any further question. So we thanks Johannes again for this nice talk.